Good morning, guys. We're going to start chapter 8 today, and it is about rational functions. And it will talk a lot about simplifying and working with ratios or fractions. And we will make sure that we review fractions in general before we deal with rational functions. So, if P and Q are polynomials, so remember that is what we've been working with all along, and Q cannot be 0 because it's in the denominator, we call that a rational expression. So we will put a function in the numerator and a function in the denominator. So let's look at this first example. F of x is equal to x minus 5 all over x squared minus 4. And we want to evaluate the first one at 6. So wherever there's an x, we put in a 6. And you can see that we have 6 minus 5 over 6 squared minus 4, or 1 over 32. If we were to look at a negative 3, we'd have a negative 3 minus 5, or a negative 8. A negative 3 squared is 9, minus 4 is 5. So evaluating rational functions is nothing different than we've been doing all along. So just be careful that when you enter something like this into your calculator, that you always put parentheses around the numerator and the denominator. So when you're using your graphing calculator, make sure that you use parentheses even when the problem doesn't show that in the original problem. So we oftentimes talk about domain, and if you recall, the domain are the values that x can be for a function. Remember that we never ever want 0 in the denominator, so the function q can never equal 0. So when we're looking for a domain, we have to look for all numbers of x that do not make the denominator 0. So let's first look at the domain of the x squared plus 5x plus 2. Now, what numbers would we have that would allow x to be equal to, the denominator to be equal to 0? So in order to do that, we set the denominator equal to 0, x squared plus 5x plus 2 equal to 0, and we realize that that is not easily factorable. It doesn't have 4 terms, so we're not going to factor by grouping. So we're going to use the quadratic formula. When we use the quadratic formula, we find out that there are two values, negative 5 plus or minus the square root of 17 divided by 2. These are the two numbers that would make the denominator equal to 0. So what we say is that that denominator excludes those values. Now, let's take a look at the example number 2, where the denominator is x squared plus 10. So we know that in order to factor that, that one works nicely with the square root property. X squared is now equal to a negative 10. When we take the square root of each side, we end up with the square root of a negative 10. Therefore, the function of g has no values of x that lead to the division by 0. Because that turns into a complex or an imaginary number, the domain of g, we would say, are the set of all real numbers. So we have no exclusions. A number is called an excluded value when the rational expression in the denominator leads to the answer of 0. So the expression 2x plus 7 divided by 5x is in its lowest terms. Although x is a factor of the term 2x, make sure that you do not cancel like this. This is not allowed. You would have to have an x in every term to be able to do that. So again, if you think of this being in parentheses, it reminds you that the only way to cancel that is if you have a 2x plus 7 in the denominator. So be very careful about that as you proceed. Now, let's take a look at the function of 2x squared minus 6x minus 20, all divided by 2x squared minus 50. And let's see if we can factor that. We still do all the same things that we did in the previous chapter. We ask ourselves if there's a greatest common factor, and there is a greatest common factor. If you divide 2 out of everything in the numerator and 2 out of everything in the denominator, we now get expressions that look factorable. X squared minus 3x minus 10, we ask ourselves what two numbers multiply together to get 10 and add together, a negative 10, and add together to get a negative 3. You can see that if we use negative 5 and a positive 2, when we multiply those, we do get the negative 10. Now let's check and see when we add those two if we get the middle term, and we do. We get negative 3. So we know that x minus 5 and x plus 2 are the remaining factors in the numerator. X squared minus 25 is the difference of two perfect squares. So we know that we have x minus 5 and x plus 5. Now, in order to simplify this, we can look at 2 over 2. That simplifies to 1. And negative 5 over x minus 5 over x minus 5 simplifies to 1, leaving x plus 2 over x plus 5. Now, what value of x would make the denominator equal to 0? That would be x could not equal negative 5. If you were to graph these on your graphing calculator, you would notice that at x equals negative 5 right here, the graph does something funky. It comes up towards it like this, and then, ooh, it can't be equal to that. And then it comes down here, and it can't be equal to that. So the x minus 5 shows you a very interesting part in the graph. It's saying the graph approaches but never actually touches that. So when we are talking about drawing it, we would use an open circle when x is equal to 5 to indicate that there's no point that a part of that graph touches it. So if a graph of a rational function has a vertical asymptote, that is, when x is equal to k, going up and down, k is not part of the domain, and it would make the denominator equal to 0. So let's take a look at the function x squared minus x minus 12, all divided by 4 minus x. Now, what number would x be in order to make the denominator 0? We're going to need to know that for the domain in a minute. Looking at the numerator, x squared minus x minus 12, we think what two numbers multiply together to give a negative 12? If we look at a negative 4 times a positive 3, when we multiply those two, we do get the negative 12. When we add them, negative 4 plus 3, we get a negative 1. So we know that we have found the correct pair. So we have x minus 4 and x plus 3. Now looking at the denominator 4 minus x, we have to start to recognize that if we were to multiply 4 minus x by a negative 1, we get negative 1, and the inside turns out to be x minus 4. That little trick allows you then to be able to cancel these two because they equal 1. You end up with x plus 3 all over a negative 1. So if you divide the numerator by that negative 1, you have negative x minus 3. Notice that by waiting to simplify and waiting to find the domain, we don't have to worry about it at all. So make sure that you go through and you factor and simplify before you make any decisions about the domain. X squared minus 8xy plus 16y squared, all divided by x squared minus 16y squared. Let's see if we can factor those. The numerator factors into x minus 4y times x minus 4y, and the denominator factors into x plus 4y, x minus 4y. So we know that these will become 1, and we are left with x minus 4y over x plus 4y. So when you're finding the quotient of functions, but if you were given the function of x and the function of g, you are going to divide f of x divided by g of x. Then we will evaluate our new function at 3. So when we want f of x in the numerator and we want g of x in the denominator, we start out now and we start to factor. 8 cubed minus 25 is a perfect difference of perfect cubes. So we end up with 2x minus 5 times 4x squared plus 10x plus 25. The bottom denominator function, 4x squared minus 25, is a difference of two perfect squares. 2x minus 5 times 2x plus 5. That allows us to cancel the 2x minus 5's and leaving 4x squared plus 10x plus 25 over 2x plus 5. So our goal is always to see if we can find factors that cancel. Now we're going to evaluate this at 3. So every place that there's an x, you substitute 3, and you find that the answer is 91 over 11. A rational model is one where we want to take two functions and divide them in order to find a ratio. So looking at an authentic description, we oftentimes want to find the percentage of something. So how many of something in P is going to be the percent. When we do percentage, you divide m divided by n, or two functions, but then you multiply your answer by 100. So let's take a look. This is the number of internet users in the United States shown for the various years. A reasonable model would be the internet is 8.4 times t plus 151.78. Remember, I of t is the number of internet users in millions since the year 2000. A reasonable model for the total population in the United States is 0.0068 t squared plus 272t plus 278.32. If the total population is represented by U of t and the users of the internet are represented by I of t, we're going to find the percentage of Americans that are using the internet by dividing the two functions. We will take I of t, we're going to divide it by U of t, and we're going to multiply that by 100. Now this looks like our previous problem, so we are going to take a look and see what happens when we substitute for t. If we want to know what has happened since 2015, remember t is since 2000, so we would substitute t at 15. When we substitute t for 15, we get an approximation of 86.63. So this model estimates that 86.6% of Americans were internet users in 2015. To find the actual percentage, divide the number of internet users in 2015 from the table and divide it by the U.S. population, and multiply that by 100, and you'd find it was 88.27%. So our result using the model is called an underestimate. It was smaller than the actual. So a reasonable model would be for the U.S. population, and t is since years 2000. What would happen if we looked at the year 2021? If we look at the year 2021 and we substitute 21 in for t, we find that 96.9% of Americans will be internet users next year. I hope this helps, and I hope you work hard on your Section 8.1 homework. And remember, I'm always here to answer questions. Have a great day.